C. This is really lesson 2 in module 17 that has to do with the strength of acids and bases. So I'm not doing the demo right now, but some acids are strong and some are weak, and that's why this is acetic acid, which is what is in vinegar. We can use that in our salad dressings and things, and it doesn't hurt us. Whereas a strong acid like hydrochloric, we definitely wouldn't do that with. If we were going to do a conductivity test, the hydrochloric acid would be really bright. And then the acetic acid would be very dim, but it has to be an electrolyte, even though it's really dim, because if it doesn't break into the ions, it's not an acid. So strong acids are going to completely ionize or break apart, and they will produce, like 100% breakup. They're really good electrolytes. The equilibrium is going to lie to the right, and I'm going to explain that in a little bit more later, because there's going to be more of the products. I'll explain that a little bit more detail in just a second. So here's the example. So this could be HA is just some generic acid. It could be HCl, but if it's a strong acid, notice that we only have the one arrow because it doesn't really go back. So it's going to break up into those ions, really 100% of it, pretty much. Sometimes we, don't forget that we can write hydronium in place of the hydrogen ion. This time, I think it's helpful to just do it very simple. So if we were going to show this in solution, and maybe draw like 6 molecules, there's one. Whoops. Oh, goodness. Here's 2. I don't know why it's not liking me. So notice how 3, 4, 5, maybe 5 is enough. So notice that they're all broken apart into the ions. A weak acid is not going to ionize like that. It's going to ionize to a very small extent. So the equilibrium is going to lie to the left, and that's because there's going to be more reactants. So if we revisit that equilibrium, so this strong acid equilibrium lies to the right because we are going to, sorry, I can't talk and write at the same time. It's going to, this is pretty much gone. So you're going to have much, almost 100% of the broken up product ions. This one, the weak, if we were going to draw the weak acid, we're going to draw both arrows now, because now you might only have like 1% of it breaks apart and 99% of it stays together. So the equilibrium lies to the left because you're going to have more of the intact acid and less of the ions. And the left side is where the reactants are. So we're going to do that similar now. Again, this is just what I just did, but breaking up just a generic acid where W is just an anion that's -1. It's, you could use any letter there, but if I tell you that this is weak, it still breaks apart. Otherwise it's not an acid, but most of it stays together. So if I were to draw it in water, I'm going to draw most of them together as a molecule. But I do want to show at least one broken apart to model that it is an acid. So there's something called the acid ionization constant. This is really, remember how we have KEQ and we have KW? This is, they're not the same, but they're all, very, very similar. And Ka values can be calculated for, mostly we do it for weak acids. Strong acids, the value is so big that it's not even, we don't even record it. So if you look at the Ka value that you get, you know, the weak acids are all going to be less than 1. You can see like here's those values and they're very, very small, but you can also then kind of compare them to each other. So if you look at this, you can see that this would be, I think, the smallest. So the hydrogen, you know, breaking up of this, you know, taking off that last hydrogen and forming the hydrogen and the sulfide ion, that is going to be not, hardly any of it will do that. So how do we write a Ka expression? Let me show you. So hydrofluoric acid is a weak acid. So we would show the double arrow this time. And then, you know, it does break up. So the Ka expression, remember, that's going to be the products molarities times or over the molarity of the reactant. Sometimes people, and I'll show you where, actually I'll just do it now while I'm thinking of it. Sometimes we put water in there, which we're going to do up ahead. And when we do that, remember how we don't include water in the equilibrium expression? So it really doesn't change the way it's written. The only difference is this would be H3O. And that's, those are interchangeable to me. So the Ka expression is always going to be the product ions over the reactant, which is the molecule not broken apart. So then when you get like hydrofluoric acid, you can see is, you know, very small. So it's less than 1, 6.3, 10 to the negative 4. Is it weaker or stronger than hydrocyanic acid? So hydrocyanic is this one. So hydrofluoric is, they're both weak, but this one is, it's stronger because it's larger than, this would be weaker between the two. But they're both weak, which means primarily the acid's going to stay together and not break up. So here is a little bit more depth on looking, and now we're going to include water. So if this is a strong acid, so now remember, we're going to set it up like with the Bronsted-Lowry. So we know that that hydrogen is going to be given up and given to the water essentially. So I'm going to get just the A ion, and then the water is going to grab that hydrogen and become hydronium. So I would pause the video and go ahead and label these Bronsted-Lowry, you know, acid and base and conjugate acid and base. So when I do this, I'll do it with you. So we know this is the Bronsted-Lowry acid. So then in this case, the water is the Bronsted-Lowry base. And you can see that the water accepts a proton and becomes hydronium. And then when you read it the other way, the hydronium is an acid. We just call it a conjugate acid because it's on the opposite side. And the A is the conjugate base because if it goes back, it's going to accept a proton and become HA. So the Ka expression is going to be always products. So the A molarity times the hydronium ion over the HA. Notice I'm not including the water. If I were to draw a bar graph of this, where I would call, you know, either the moles or the molarity on the Y, and then, you know, I would have the HA, the hydronium, and the A. So really there's nothing here, or it's been very negligible, and then you would have equal higher numbers of moles of the ions since it's strong. One last thing is we talk about the equilibrium. We've talked about this already, but I'm going to reiterate. The equilibrium is going to lie to the right because you're going to mostly have this, the products. So equilibrium lies to the right, and that means this conjugate base right here, that conjugate base is going to be weak because it's not likely to go back and form HA. If it does, it'll just quick break apart again. So it's always going to be that way. The strong acid will be paired with the weak conjugate base. So similarly, we can do that same thing for a weak acid. So here's our Bronsted-Lowry acid, and it's can't spell. That's really an L. Bronsted-Lowry acid. It's going to donate its hydrogen, and it's going to become W, the ion, and then the water is going to become hydronium. So I'm going to write this nicer for you. So this is the Bronsted-Lowry acid. This should always be the base, and it is. If you read it going this way, it is going to accept a proton. Then if I read it the other way, going backwards, this is an acid, and this is a base, and then we just call them the conjugates. So the Ka expression is going to be, and this doesn't matter what order you put these, but, so it'll be the anion and the hydronium over the weak acid molarity. The bar graph is going to be, again, moles or molarity. This time HW and then the hydronium and oops, I have a typo, that should be W. This one's going to have, most of it is going to be the intact, and then just a very small amount of these ions. And then thinking about equilibrium, it lies to the right, because don't use that, because it wants to, this doesn't really break up. So you're mostly going to have the HW. So equilibrium lies to the, left. And then that makes this conjugate base is strong, and it'll always be that way. The weak acid will be paired with the strong conjugate base. It's very likely for this W to go back and accept a proton and become HW. That's what makes it strong. So the strong acid is always paired with the weak conjugate base, and the weak acid is always paired with the strong conjugate base. And then this kind of just summarizes all of that again. If like if we were going to draw our tie lines, this is our acid, our base. This one's a strong acid. This is our conjugate acid and our conjugate base. So this is going to be, the equilibrium lies to the right. That means this conjugate base is weak. It's not likely to go back and form the HA. So the conjugate base is not likely, and that makes it a weak base. And then similarly, here HW and W. So this is the equilibrium lies to the left. So this conjugate base right here is likely to accept a proton and go back to the left, which makes it a strong base. And these further slides I'm not going to talk about them just because I think I've over-explained already, but these are definitely in the slide deck. Everything we said is true for bases too. Strong bases break up 100%, weak bases do not. And, there are actual KB calculations and expressions. We're just not going to cover those. But if you were to, look at the values, you should be able to see that the weakest of the bases here is the aniline at the bottom. So that's all I have. I hope that helps.